Yeah, it's still mostly charged. So.
By the way, Ivo is leaving his hotel already tomorrow, but it's reserved until tomorrow.
Okay.
So I was saying I could just take over.
Oh, okay. Is
So
this
then-
anything that you need to be sort of officially
No,
processed?
I'm just saying because I sent an email earlier, and then I could just I don't know if you were if you were checking those emails or anything, so just to verify.
Okay.
That's
Sounds
we're
good.
gonna do that. So.
Has it been okay the last few days?
Yeah, it has. I have a nice view on a pond.
Oh, nice.
Yeah. But
Ready to be introduced? All right, let's get started with our last lecture of the day. So this will be our last lecture from Andrea about asymptotic symmetries.
thank you. Okay, so I just realized the mic was not on, so too bad. Okay, so we address this with polarizations. I've given you some favorite polarization vectors, plus minus, epsilon plus minus before. It's quite natural to choose them as z derivatives of the q mu's, maybe with some square roots of 2 to normalize them appropriately. So this is the polarization vectors that I used yesterday. And I doubled them in order to get polarization tensors. Now it turns out that these polarization vectors don't transform nicely on the SL2Z, but we can correct that by shifting them. So I define new polarization vectors M, which are shifted polarization vectors, and they get shifted by certain inner products of the polarization vector with the spacetime vector and the null vector Q with the spacetime vector. And this polarization vector turns out to have definite conformal dimension 0 and spin plus 1. And then similarly, we can do this for the negative helicity. Let me call it M bar mu. And this has also delta equals 0 and j equals minus 1. And then with these ingredients, the scalar wave function and these polarization vectors, which have definite spin, we can then construct spinning wave functions. So the spin one wave functions, let me omit the spacetime index. So the ones with positive spin are now obtained by taking one factor of this polarization vector and the scalar wave function. And similarly, the ones with negative spin are obtained by taking this other polarization vector. And these solve Maxwell's equations. And now it's also very easy to obtain the spin 2 wave functions. Positive spin, I just take 2 copies of this polarization vector. And I didn't plan on saying anything about this, but since Cliff talked about the double copy, this is a very simple instance of the classical double copy. First, we start with the zeroth double copy, which is the scalar wave function. Then we double copy it by, well, we compute a single copy by adding this vector m, which is the so-called Kerr-Schild vector, which is null and geodesic with respect to, well, the flat metric here. But also then when we double copy it to have 2 factors of this Kerr-Schild vector, it's null and geodesic also with respect to a metric G that you get by taking the flat metric plus adding this H. And now I'm tempted to make a little side comment and talk about some maybe a bit more interesting wave functions that you actually all know. So this is a wave function that has some function, some logarithmic function of x squared and a delta function in q dot x. So this is something, so in principle, we could add logarithms of x squared. This will not change the conformal dimensions and the spin of these wave functions, since this is a Lorentz scalar. And I can also get delta function if I pick this conformal dimension up there to be 1, and then add a plus I epsilon, and the same thing with a minus I epsilon, and then I take the difference and take epsilon to 0. So this is like 1 over x plus I epsilon minus 1 over x minus I epsilon. This is a delta function. So this is how we can construct these wave functions. And then we can construct from there spin 1 wave functions by multiplying with this original null vector q that I had, and also spin 2 wave functions. And does anybody recognize what the spin 2 wave function gives rise to? You might have seen this in your GR course. So if I start with a flat metric and I add to this q mu, q nu, log of x squared delta q dot x. This is the Eichelberg-Sechsel metric. Which is a very interesting metric that has can be constructed via some double copy procedure, as we just did. And what's very nice is that this actually transforms with definite conformal dimension in spin on the SL to Z. So maybe I should have said this here, the scalar wave function, transforms with dimension 1 and spin 0. The spin 1 transforms with dimension 0 and spin 0. And this guy here transforms with dimension -1 and spin 0. And this is the reason why I kept writing in general, not just the helicity label or the J label, but also the S label, because this is still a spin 2 particle from the point of view of the bulk, but in 2D it carries 2D spin 0. So it's very nice that this basis, this boost basis, which lets us think that there's some two-dimensional description of four-dimensional physics in the bulk, has interesting, physically interesting metrics, or in general solutions. So this one would be the electromagnetic shockwave solution, that transforms as a natural object in this two-dimensional theory. So one reason why this is interesting is we could think of scattering on top of backgrounds. And this object already transforms nicely on the SL to C. So this is a natural background on which to scatter. And nice things happen, but I don't have time to explain them. OK? So now I've told you how to construct general spinning wave functions that are boost eigenstates. And now I want to come back to symmetries. So I told you that when delta takes certain integer values, this should have something to do with symmetries. So now let's look at these special values. So let's look at the ones with spin, which are the ones where we have asymptotic symmetries. So let's take the spinning wave function and look at the delta equals 1 case. And let me put back the spacetime index. It turns out that when you take this spin 1 wave function and set delta to 1, then this can be written as a total derivative of some function. Let me call it lambda gauge. And this smells like a large gauge transformation, right? So we had when you have the gauge field, we talked about AZ going to AZ plus dz of epsilon. If epsilon is a function of the angles, then we have a large gauge transformation. So this kind of smells like it. And indeed, this lambda gauge, if you take R to infinity, actually becomes epsilon, the one that we had yesterday. And what about gravity? So the dimension 1 spin 2 wave function also turns out to be special. It's a diffeomorphism. Let me psi 1. And it so happens that this can also be written as a total derivative of some function. Let me call it lambda gravity. The fact that it is a diffeomorphism, if this diffeomorphism is suitably chosen, then this could be one of our asymptotic symmetry transformations. And indeed, this case turns out to correspond to supertranslations. And this function here, lambda gravity, if you multiply it by 1 over r and then take r to infinity, this corresponds to our function f that we had yesterday in the case of supertranslations. So somehow in these conformal primary wave functions, we recover the diffeomorphisms and large gauge transformations that we spent 3 lectures talking about. Now there's another diffeomorphism that arises when delta equals to 0, also in the spin 2 case. Let me call it psi 0. And there exists yet another diffeomorphism when delta equals 2. Now, this seems a bit too much because we just have superrotations left, in principle, at least from the last 2 lectures. So it turns out that these two both have to do with superrotations. But one has to do with these Virasoro superrotations and the other one with the diff-S2 superrotations. So let me maybe add here, we had talked about a special function yesterday, which was the one that if you start with the large gauge charge and you plug that in the large gauge charge there was a derivative. If you hit this function with a total derivative, you get a delta function. You can get rid of the sphere integrals and recover the soft theorem. Similarly, in the case of gravity, we had another special function, z bar minus w bar over z minus w. And the super translation charge had 2 derivatives. You hit this function with 2 z bar derivatives. You get a delta function. You collapse the sphere integral, and you recover the leading soft graviton theorem. Here we talked about 2 different types of functions, or vector fields rather. We had one vector field that violated the conformal killing equation at isolated points. So this was something that looks like 1 over z minus w, or is an holomorphic function up to singularities. And there was another one that was not meromorphic. And at the end, I talked about a vector field that if you hit it with 3 derivatives, which is what appears in the superrotation charge, then this becomes a delta function, and you recover the subleadings of graviton theorem. Now, this one was the vector field that was associated to Virasoro symmetry, and this is associated to diff-S2 symmetry. And these 2 wave functions and their associated symmetry parameters are actually related. And they're related by some other integral transform in this pseudo-celestial conformal field theory that's called a shadow transform. And this is something ubiquitous in 2D CFT. So this is now an integral transform on the sphere. So d squared z prime that comes with a certain kernel, z minus z prime to the power 2, 1 minus h, and z bar minus z bar prime to the power 2, 1 minus h bar, where the boost weight is h plus h bar, and the spin is h minus h bar. And what this transform does in 2D CFT is it takes an operator with dimension delta to another operator with dimension 2 minus delta. Or in general D dimensions, this 2 would be replaced by D. So this is an ubiquitous transform in 2D CFT. And how it arises here is that the subleading soft graviton theorem, which is associated to a superrotation with this non-meromorphic vector field, can be brought into a form that looks more like a CFD by performing a shadow transform. So I didn't tell you this yesterday, but when we wrote down the subleading soft graviton theorem, I also said that you have to smear it a little bit on the sphere with some special function, and then it looks like the correlation function of a stress tensor. This is precisely this transform. So here, if you plug in h is minus 1 and h bar is 1, then this is this function that we had yesterday, which was 1 over z minus z prime to the 4. So this is all related and all sort of entangled. The asymptotic symmetries, how they arise from the point of view of the 2D theory, and how they connect to soft theorems. Maybe now is a good time to ask if there are questions. Yes? This one?
Yes. For instance, I am confused. CFT will differentiate between quasi-primary and primary. So how these quasi-primary transform into superrotation.
Sorry, say it again.
In CFT,
yeah,
we differentiate between quasi-primary.
This is a quasi-primary, the phi's that I'm talking about.
So here they are quasi-primary.
Mm-hmm.
So how those transform under translation and superrotation?
We'll talk about that. The question was how these primaries transform under superrotations and supertranslations. We're going to do precisely that. We're going to study how what these symmetries are from the point of view of 2D CFT, and then how they act on some operators or wave functions of some definite delta, the ones that I just told you about. And in order to do that, let me recall something else that you already know. So I'm applying Fermi's rule twice, hopefully. So hopefully you derive joy in hearing things that you already know. So symmetries in QFT. So what are symmetries in QFT? So we have conservation equations for operators that define symmetries. Once we have such operators, we can construct Noether currents by a suitable contraction of these operators with some parameter. Let me call it epsilon. And then the conservation of the Noether current and let me do this in general. So in general d-dimensional QFT, I have some index A from 1 to D. Here's a Noether current, JA of X. This has to be 0. And now since the operator is conserved, the conservation of the Noether current implies a condition on the parameter. And this will be very important. And now actually we don't just have that the divergence of the Noether current is 0. This is 0 up to contact terms. So in correlation functions, if you put the divergence of a current together with some other operators, then what you get on the right-hand side is not just 0, but you get contact terms, which arise when the insertion of the current X gets close to the insertion of the other operators. And this is your word identity. And now, once you have built your Noether current, you can construct charges. So these will be topological surface operators. See how I sneak in the topological here to get the attention of some of you. So here we'll have some charge Q sigma that we integrate over some d minus 1 dimensional surface in RD. Let's say our CFT lives in RD. And this is the surface element multiplied by the normal to the surface sigma and the Noether current. And now we understand this surface operator as being inserted in a correlation function. And when there are no other, when you deform the surface in such a way that you don't cross any other operator insertions, then we say that Q is conserved. Now what you can do is you can, in this word identity, we can replace the divergence of the current by the charge. So Q sigma, where sigma is the boundary of some region R, I can write this via Gauss's law as some volume integral of the divergence of the Noether current. And then I can write this word identity where my charge now surrounds, so the region sigma surrounds the insertion of the operator I. And this just gives you the variation of the ith operator. So the insertion of the charge in the correlation function boils down to the variation of the ith operator. And now if you pick this region such that all operators insertions are, all operators are included, then we get 0 on the left-hand side. And this is what we mean by symmetry, or symmetry transformation. And this is the very conservative meaning of symmetry that I will use in the following in order to classify what all the symmetries in celestial CFD are that arise from soft physics. So what we're going to do now that we have sort of established some sort of CFD structure, which has underlying the action of the Lorentz group on the celestial sphere, as well as this X extension through superrotations. I'm now going to use conformal representation theory to put some structure here to introduce some organizing principle for all the symmetries that have to do with soft theorems or equivalently asymptotic symmetries. So we're going to look at what are the conformal multiplets in celestial CFD. So what we want to do is we want to organize the celestial CFD data in representations of SL to Z. So let me remind you of something that you also all know, which is that if I have a primary with weights h and h bar, this means that L1 acting on it is 0, same as L bar 1. And we can construct descendants by acting with the L minus 1s, say to some power k, and the L bar minus 1s to some power k bar. And the L minus 1s in 2D CFD, where I'll work with z and z bar coordinates, and I have derivatives d, z, which I will also denote by d for del, and del z bar by del bar. These guys are just del to some power k and del bar to some power k bar. Okay? Now then, if we have such a descendant, let's call it h prime and h bar prime, that we obtain by taking L minus 1 to the k and acting on h and h bar, then this is called a primary descendant. If L1 acting on this guy vanishes. And when does this vanish? This I leave as an exercise to you. It vanishes when the weights of the primary is 1 minus k over 2, where k is a positive integer. And h prime, which is the weight of the descendant here, the primary descendant, is 1 plus k over 2, which is nothing but 1 minus h. And this is sort of a reflection of weights. How do you see that? Well, here we're taking k del derivatives, and this will increase the weight by k. Okay? So these will be the the main characters here. So the question will be, what are all the primary descendants in CFT? And we will use as input the conformal weights that are told to us by soft theorems. So once we start with the primary and we compute the descendants and then check when the descendants are primaries, we get some conformal multiplet structure that roughly looks like this. So here I'm drawing the del bar derivatives in this direction and the del derivatives in that direction. So you may start with some primary operator that has weights h and h bar. You take k holomorphic or k bar antilomorphic derivatives, and you go to some descendants. And at some point, there may be a descendant that is a primary, which is what these corners are. And then you may have a primary descendant like this, and you can also do this for the L bars. And then you may have a descendant of those primary descendants, which is the same one. So you construct a primary descendant like this, another primary descendant with the L's replaced by L bars. And then these two primary descendants may have another primary descendant when both these conditions are satisfied. And then you can end up with this descendant down here, which is also a primary descendant. Now, if you want to catch people's eye, you have to give things a cool name. So we call this conformal multiplets, celestial diamonds. And I think at some conference, there was some pun made about diamonds in the sky or something. So, you have to give things a cool name. Now, it turns out that if you want to classify these primary descendants in CFT in general, not restricted to these celestial CFTs, in 2 dimensions, there are 3 types of primary descendants. Very originally called type 1, 2, and 3. And how are they distinguished? They're distinguished in a way by looking at the spin of the descendant with respect to the parent. So if the spin of the descendants is smaller, bigger, smaller, or equal to the spin of the parent, then we talk respectively of type 1, 2, and 3. And the structure here is sort of schematic, how type 1, 2, and 3 arises, or what the conformal multiplet looks like. So you have type 1 primary descendants that live on these upper sides of these diamonds, type 2 primary descendants that are down here, and then the type 3, where you have equal spin between the parent and the descendants, they look like this. They look like a 0 area diamond. And now what our task is, in order to find all the symmetries in celestial conformal field theory, is we take as an input the soft theorems and then use this classification of primary descendants in order to figure out what they are, what kind of asymptotic symmetries they correspond to, or what soft theorems.
Just to tell you, we're about 15 minutes.
Great. All right, so the rule of the game is now to find all the primary descendants. And then once you have the primary descendants, we go over here. We go back to our basic CFT knowledge, and we find from the soft theorems operators that are conserved. These will be operators with special conformal dimension. From there, we construct Noether currents by introducing some parameters. Then we use the conservation of the Noether current to put a condition on the parameter. And then we construct topological charges. And then we want to relate these topological charges to the asymptotic symmetry charges that I introduced yesterday. And this will then tell you what the symmetry group is. So now this leads me to what I will refer to as conformally soft theorems. And this is another fancy name for the energetically soft theorems. So we said we go from the energy basis to the boost basis. So we go from energetically soft theorems to conformally soft theorems. What is conformally relates to the conformal boost weight. So how do we do this? We had a question before of how we Mellin transform something that has 0 energy. So this is our Mellin transform. And now in our energetically soft expansion for the amplitude, we have some powers of the energy, right? So let me just call this K. And this, what K is, the value of K is related to at which order in the energetically soft expansion you're looking. So the leading one starts at the pole, then the order 1, power 1, and so on and so forth. And now if you look at the Mellin transform of these powers in omega, what you will find is that the powers in omega translate to poles in delta that are related to this value K. So K in the soft theorems had values -1, that was the pole, 0, +1, etc. So this is the order 1 over omega, order 1, order omega. And what they relate to are conformal dimensions or boost weights of +1, 0, -1, etc. And these are precisely the boost weights that I discussed before at the level of the wave functions, where we found large gauge transformations and diffeomorphisms. So we looked at the first two here. Okay? So you pick your favorite soft theorem, you Mellin transform that power and energy, that tells you at which operators, for which operators you should look for in this celestial conformal field theory, what dimension this operator has. And now we're going to run through this, what I'm just erasing. We're going to run through the usual CFD procedure in order to construct Noether currents and charges. So let's talk about gauge theory first. We have a conformally soft theorem, conformally soft photon theorem, which is nothing but the usual soft photon theorem, but now expressed in this boost weight basis. So I'm instructed, because there's a pole for the soft photon, I'm instructed to look for delta equals 1. So I will take the limit of delta goes to 1 of my Mellin transformed amplitude that had a number of hard particles plus the soft photon. So the soft photon has j equals 1, and I will take the dimension to 1. And then there are the dependence on the hard particles, which I'll just denote by the dots. And we are instructed via this formula here that we should look for poles at delta equals 1. Now let me put this on the other side, so delta -1 on this side. And what I will then find is the soft photon factor, now stripped of the energy, times, there's a +1 here, times the amplitude without that soft particle, but now expressed in the boost basis. So this was what I called S hat 0 yesterday. And already yesterday, we saw that this kind of looked like the insertion of a current. And now we know that the Mellin transformed amplitude is a correlation function of operators with definite delta. And spin. Okay? And we now know what this guy is. So this guy is a dimension 1 operator. Dimension 1 and spin 1. So this is a U1 current, a U1 Kac-Moody current, to be precise, in this two-dimensional celestial conformal field theory. And you see by looking at the correlation function of this current that it is conserved in the sense that the anti-holomorphic derivative hitting it gives 0, or 0 up to contact terms. Okay? So now that we have identified this conserved operator, we can now construct the Noether current. And I mean, this you have seen in your, well, CFT course or whatever, but let me just illustrate this. It will be more complicated for the leading soft graviton theorem. So let me just illustrate this for the soft photon. So we construct the Noether current by multiplying this U1 current by a parameter epsilon. We know that we demand that the Noether current is conserved. J is already conserved, so this means that there's a condition on this parameter epsilon, which says that it is holomorphic up to poles. So this is solved by epsilon being a function of z, and we can expand this in powers of z. And the special parameter that we talked about a couple of times is also an example of that. Now that we have a Noether current, we can construct the topological surface charge. Since we're in 2 dimensions, this is given by a contour integral over the Noether current. The Noether current is just given by epsilon times the U1 current J. And from this, we see that we get an infinite tower, if we plug in our expansion in epsilon, an infinite tower of charges Qn. And this infinite tower, so when epsilon is 1, we just get the global charge. But if epsilon is not 1, if epsilon is any function of z, we get all the infinite enhancement, which corresponds to large gauge transformations. Now I've introduced this topological surface charge, but it's also not hard to see that this charge is actually related to the soft charge that we talked about yesterday. And the way to see this, let me illustrate this. So let me write this a little differently. So let me write this as an integral over a region, d square z, of del bar of this Noether current, epsilon j. And now if you look at some region R where epsilon has no poles, you find that you can write this as an integral over the sphere, epsilon times del bar j. And we didn't go into the details yesterday, but this current, J, can be expressed as the integral over the future null boundary of some component of the field strength, the 1 over r squared component of the field strength. Well, let me say this. This can be explained in terms of the uz component of the field strength, and the uz component is related to the ur component, the 1 over r squared term of the field strength, via the constraint equations of Maxwell theory. And where does this ur come from? This came from the original definition of our U1 charge, epsilon star f, where star f is nothing but d squared z fur, the 1 over r squared term. So there's some series of steps that leads us to this formula. And so this just says that this is the soft charge, soft part of the charge, which was linear in the fields. There was also the hard charge, which contained the current or the stress tensor and was quadratic or in general nonlinear in the fields. And that charge arises because the way that Q sigma acts on fields is, I think I erased it, if you look at this charge inserted in a correlation function, in general it gives you the variation. And that's how charges or symmetry generators act on hard particles, and that gives rise to the hard charge. So all of this maps into each other. We have the large gauge charge, which we could split into a soft piece and a hard piece. And this is also related to the usual construction of topological surface charges in now the 2-dimensional theory on the boundary. I think I have 5 minutes left. Yeah, let me maybe just say, so I've just gone through the very simple example of the soft photon theorem. We can also do this for the soft graviton theorem, the leading and subleading one. The construction for the leading of graviton theorem is very similar. You also have seen it in your CFD course in principle, because there J will just be replaced by the stress tensor. And then you go through the steps. You also find that there's a symmetry parameter that has to be holomorphic. And then you construct the charge, which corresponds to the LNs. And then for the leading soft graviton, that's actually a little bit more funny. And the construction of the Noether current is a bit more complicated. But you can also go through these steps. And you find that the topological charge that you construct is related to the super translation charge. So then in the last final minutes, let me just make a few comments here. So just to summarize, we talked about asymptotic symmetries, how they're related to soft theorems. And now in this lecture, I have shown you how you can think of amplitudes as correlation functions in subputative codimension 2 boundary theory. It has some CFD features, but it also has more exotic ones, which I didn't have time to talk about. But just for the purpose of symmetries, we can now use this powerful tool of CFD in order to classify what are all the symmetries. I've given you the recipe. You look for all the primary descendants. You look for the delta of the special operators, which is told to you by soft theorems. So you look at whatever soft theorem you're interested in. You figure out what delta is. You look at this classification. You find an operator. You know that if you map the soft theorem to the boost spaces, it corresponds to a correlation function of the special operator. Then you hit it with enough derivatives, you will find that it is conserved, that the right-hand side is 0 up to contact terms. Then you can construct from there a Noether current with some parameter. The conservation of the Noether current gives a condition on the parameter. You construct a topological charge, which contains this parameter. And this will give you a constraint. So there are certain symmetry parameters that you get. For gauge theory, we had that soft photon. This condition is that del bar of the symmetry parameter is 0. For the leading soft graviton, this condition is that del bar squared is 0. This is a non-standard conservation equation compared to what you're used to in CFD, which makes the leading soft graviton and super translations a bit more interesting. So that is leading. The subleading soft graviton actually has a third order conservation equation. But this conservation equation is related via a shadow transform to a more normal looking or more standard looking conservation equation or conditional parameter. And this one gives you the stress tensor, while the upper one gives you what you might call the shadow transform of the stress tensor. Now you could go on and you could go to more and more subleading soft theorems and you will get higher and higher conservation equations or conditions on these parameters. And the ones that I've talked about here in this above classification are all of type 2. If you go further down in the soft expansion, you will also find type 3 and type 1. And one very interesting aspect of these soft operators at more and more subleading order in the energetically soft expansion or at more and more subleading powers, values of the conformal boost weights, more and more negative. If you look at the algebra of these operators, you find that they satisfy one. So one thing that I didn't have time to talk about is you can ask, well, what does the operator product expansion in celestial CFD look like? Well, what does that mean? You have a celestial sphere. You want to take two operators close. That means the position in Z, so Zi and Zj on the celestial sphere comes close. What does that mean from the point of view of amplitudes in the bulk? It's when two particles become collinear. So via the collinear limits of amplitudes, you can figure out what the operator products expansion is in the celestial conformal field theory. And the OPE for symmetries or for soft operators is the same as computing commutators. And if you compute the commutators of all this infinite, semi-infinite tower of soft operators, you will find that they satisfy nice algebra. And in the case of gravity, this algebra is called the W1 plus infinity algebra. And now I think I'm out of time, so let me just wrap up by saying that there's many interesting connections to many different fields. For example, this symmetry algebra was actually originally found in the context of twistor theory. And there is interesting links to twistor theory. Obviously, there's an overlap or link or interest with amplitudes, but also with GR, gravitational wave physics, in the context of memory effects that are associated to these soft theorems and sort of special operators in the celestial CFD. We know now that there's a semi-infinite tower of special operators. So one question is there an infinite tower of infinite dimensional symmetries? And are there memory effects that are related to these ever more subleading soft theorems or more negative boost weight operators? And what the full meaning is of these symmetries and the symmetry algebras. So there's lots of interesting connections. Well, I look forward to welcoming you in this field. Thank you.
Questions?
I have a very basic question. I'm not sure how to think about the fact that the boundaries could mention 2.
Mm-hmm.
Do you have any comments on that?
Yes. So if
Can you repeat the question?
Oh, the question was, this boundary theory is codimension 2. If you know anything about ADS-CFT, you learn or you're taught that holography relates a theory in the bulk with a theory of codimension 1 in the boundary. Now, why do we have codimension 2 here? What does that mean? So if you remember, in the very first lecture, we talked about how the induced metric on the null boundary is degenerate. And I've told you that this is called Carolian structure. So one thing that you could ask is, if you have a bulk operator at point X, how can you map it to some boundary operators? That is sort of part of the holographic dictionary, right? You want to map bulk objects to boundary objects and vice versa. And the natural thing is to say, well, I'll just push it to the boundary, right? I just take R to infinity in some suitable way, and I push this operator to the boundary. Now, what you then have, if the bulk is 4-dimensional, you have that the boundary is 3-dimensional, right? So what you would get is, if you start with some operator in the bulk, and you do some suitable large R limit, you get some operator on the boundary that is now still dependent on 3 coordinates, u, z, and z bar. And this would be a Carolian field that lives on this Carolian null boundary. Now, I told you Carolian boundaries is like the speed of light to 0 limit, so there's some strange things that are sort of non-standard from our usual quantum field theory point of view, and which have to do with the fact that it's not that there is no standard notion of time on these boundaries. But what you can do is you can say, well, let me just integrate over the boundary, and let me call this integral transform L. If you integrate from -infinity to +infinity over u with the power u to the minus delta, then you turn this bulk operator that you push to the boundary into an operator that now only lives on the boundary. And this operator carries this boost weight delta. So let me maybe draw another picture here to answer this question. So these boundary operators that I've talked about, one way to understand them is by pushing bulk operators to large distance and then integrating over the boundary position, which is the retarded time. That introduces for you another label which precisely corresponds to this boost weight. So I've thrown at you several integral transforms over the course of the last 3 days. We started talking about we talked about soft terms and so on, which are described in an energy basis. And I've told you that if you Mellin transform, you go to the boost basis. But we could also think about, let's say, memory effects, which are usually described in a position basis. And we can use this integral transform that I've just written down here to go to the boost basis. And then obviously omega and u, you know how they're related. They're related via Fourier transform. And so there are 3 very convenient bases for discussing scattering and the infrared physics of scattering, which is the energy basis that's suitable for discussing soft theorems, the position basis, which is suitable for discussing memory effects, and then what I would like to argue is that the boost basis is suitable or most suitable for discussing symmetries. And the reason for that is that we have now all the sort of tools or very powerful tools of CFD available in order to figure out what those are. And we can classify what the symmetries of disputative celestial CFD on the boundary is. OK, that was a long answer, but I hope that replies to your question.
Okay, well, in view of the time, I think we should probably stop here. This is the last lecture for Andrea, so let's give her one more round of applause for a very nice lecture series. And we'll see you tomorrow morning at 9 a.m., as usual.